Hello again, and thanks for choosing to watch my plain talk version of how distribution capacitor banks compensate for inductive loads. My name is Tom Sullivan, and in this video, we'll look at three types of loads that are connected to electric distribution circuits to learn why electric utilities use capacitors. We'll start with the most common type of residential loads, which we'll refer to as active. They are also called real or resistive, and there are many different examples of this type of load. In this simple circuit diagram, we have just one source and one active load connected together. The source delivers electrical energy to the circuit, and the active load removes that electrical energy and converts it to some other useful form of energy. In this case, we'll say that the active element I've drawn here is a water heater, converting the electrical energy to heat to produce hot water. I've also placed a blue arrow in the middle of the circuit to depict this continuous flow of energy from the source to the load. The next category of load to discuss is called reactive, which act very differently than the active loads we just saw. True to their name, reactive loads, such as the inductor and the capacitor shown here, spend half their time removing energy from their circuit and storing that energy in their fields, a magnetic field for the inductor and an electric field for the capacitor. And the other half of the time is spent returning that stored energy back to their circuits. Unlike active devices, these reactive devices only temporarily remove and store energy from their circuits and then simply return that energy back to those circuits. At the end of this cycle, the net transfer of energy between the source and the reactive device is zero, because all the energy delivered to the circuit by the source is removed, stored, and returned back to the circuit and the source. Again, I've placed blue arrows in the middle of these circuits to depict this exchange. And please note that these arrows point in both directions in each circuit. To account for their action of removing energy and storing it in their field, and their reaction of returning that energy back to the circuit. Notice too that the blue arrows in the inductor's circuit are in the opposite direction of the arrows in the capacitor's circuit. This is done to show that their actions in real time are opposite one another. When the inductor is removing energy from its circuit and storing it in its magnetic field, the capacitor is returning the energy that had been stored in its electric field back to the circuit. We'll soon see how this out-of-sync activity can be used to our advantage. Our last category of load is comprised of loads that are a combination of the first two, active and reactive. Motors represent the largest type of these loads. They are different from our first two categories simply because they are a combination of both of them, containing active and reactive elements. We'll use this elevator motor as our example because it needs reactive power to create the magnetic fields that allow it to spin, and it needs active power to lift the people from one floor to the next. Let's look at some feeder diagrams to discuss the nuances of these different loads. To start, we'll look at a simplified diagram representing the distribution feeder serving our active water heater customer. In real life, this feeder would be a few miles long and would serve hundreds of customers. But for our purposes, we'll just show our water heater customer's pole and imagine that it's near the end of the circuit. It draws active power, so that energy must be supplied by the source feeding its substation and has to flow the full length of the feeder all the way down the line to the customer's load, as we can see here. An important point to be made here is that the current flowing through the feeder's conductors generates heat in those conductors, which is lost into the air. Perhaps surprisingly, these losses represent the largest losses on a utility's electric system. In the case of active loads, there's nothing that can be done to minimize these losses other than properly sizing the conductors. Now let's look at our customer with the elevator motor load. To simplify our comparison with our water heater customer, we'll say that the motor is drawing the same amount of active power as the water heater, and also that same amount of reactive power too. Again, this combination of active and reactive current flows from the substation all the way down the line to the customer. Surprisingly, however, the losses from conductor heating in this circuit will be much more than twice as much as the losses in the water heater circuit. Luckily in this case, however, the losses caused by the reactive current flow can be compensated. Thinking back to our discussion about inductors and capacitors, we've already revealed the solution to these losses. We'll just put a capacitor with the same reactive draw as the motor's reactive draw on the pole right outside the customer's facility. In this slide, that's exactly what we've done. We've added a capacitor on the customer's pole that compensates for the motor's reactive draw. Because the capacitor and the inductor are the same size, when the customer's inductor is removing energy from the circuit to store in its field, the capacitor is returning that same amount of energy back to the circuit, and vice versa. So they simply exchange their stored energies back and forth, and this leaves the source only having to feed just the active motor load. This means that the source ends up supplying just the minimum amount of energy, the active amount, and the losses are minimized to the same amount as in the water heater circuit. To summarize then, while it may seem like a small point at first, the result of adding capacitors to compensate for inductive loads is the elimination of the losses that the extra reactive current wastes in the conductors. And this results in a huge savings for the utility. If you want more information than this video provided, or if you'd like to ask questions about the material in this video, or participate in a group discussion about the information presented here, please visit theelectricclassroom.com.